k, and our grid size is going to be delta by 2, where delta is the closest point we have computed, closest distance we have computed so far. Okay? And the rest of the logic is very similar to what we have said before. At most 1 point per square, because the closest distance is delta. Therefore, within a distance of delta by 2, you can't have 2 points, right? Because otherwise, then they are closer than delta, right? So you can't have more than 1 point per square, and points closer than delta will be at most 2 squares from each other, because otherwise, well, you're too far. And so only that means because you have to consider only 2 squares from where you are, that is a linear number of that's a constant number of squares, right? So the number of squares you have to consider for checking if there is a closer element, right? So again, you're not trying to compare this element with everything in the world, right? You're trying to see, okay, is there any element that's closer than delta, the smallest distance that you have computed, right? For that, I have to go to my cell, and then I have to look at cells that are at most a distance of 2 from me, and within that I will be able to find it, right? And how many are there? Maybe something like 16 or so, right? It's a constant number. Okay? So, but the catch here is, of course, each time I update the delta, right? Now I have to rehash, right? Because my hash table, the cell sizes are based on the distance delta that I've computed so far. So my biggest cost is that every time I hit a point and I reduce my closest distance, I'm going to have to rehash, and that's could be expensive. Okay, so correctness is more or less clear, right? So you have a very simple algorithm. You are going to go use this hash table, look it up, look at its neighbors. If you find anybody closer in those neighboring cells, then you're going to update delta, and then you're going to continue, right? So correctness-wise, this seems quite simple, right? So the only issue really is performance, right? So what is the performance? So let's look at the performance, and as I said, the performance is really affected by how often do you have to rehash, because if you decide, let's say you processed k points, and now you decide you have to rehash, then, okay, let's go through this a little bit more carefully. So you process k points, put them into these hash table cells. K plus 1 point arrives, right? So ideally, you would want to spend only constant time for that k plus 1 point, right? But if the k plus 1 point is closer than delta to some other point, then you have to spend time proportional to k, right? Because you rehash all the k elements we have seen before. So if you do this carelessly, this becomes a k-square algorithm, right? And you would like it to be k or k log k, or n or n log, order of n or order of n log n algorithm. But if you do this stupidly, and then you end up, or let's say you get very unlucky, and each time you have to, you consider the k point, everything has to be rehashed, well, then you will have a k-square, order of n square algorithm, right? So what we want to do is, can we use some randomization to make sure that the expected number of rehashes is small enough that you can retain something like, n square, linear or n log n type of time. Okay? So we will just look at the insert operation, because it looks like rehashing is the main cost. So if you just look at the total number of insertions into the hash table, that should give us a good bound on how long it takes. Okay? So let's say how this is true. Okay? So again, what is the probability that you have k elements all put into this hash table, and now you need to rehash everything because your distance has become smaller. Smallest distance has become smaller than delta. Then the probability is 2 by I. Why? We will just go through that. Okay? So let's say P1 to Pi be the points we have processed so far, right? And let's say some P and Q among these are the closest pair, right? Now, rehashing is needed if, when you add Pi, right? rehashing will be needed if pi is either p or q. Right? If it's one of the closest pair among the pi, that's when addition of pi is going to require rehashing. Correct? If let's say your process P1, P2, P3, P4, P5, and let's say you are adding P6, right? And if among these two, if these 6 points, let's say the closest pair is these two, right? Let's say P3 and P5, then addition of P6 is not going to require you to rehash, right? Because by the time you get to P6, the closest distance between these two, and you already hashed using that distance delta. Therefore, when you find P6, you'll find that P6 doesn't change the closest pair, right? And so you don't have to, it doesn't change the smallest, the closest pair distance deltas we have computed so far. So there's no need to rehash, right? So you say, okay, I don't have a rehash. So that is what this is saying, right? So the last point you add, if it's one of the closest pair, then you will need to rehash. If it's not one of the closest pairs, then you don't need to rehash. Okay? Now what's the probability that pi is one of the two?
2 by and 2 by I.
Right. So it's just 2 by I, right? Because the closest pair could be any one of these I points, right? Any two of these I points could be the closest part of the closest pair, or any two of these, any two of these I points could be part of the closest pair. So the probability that the ith element is one of them is basically 2 by I, right? So that's what this is saying, right? The theorem is simply saying that the probability is 2 by I. Okay? So now we can say how many insertions are required, right? So we can do this very easily because let's do this calculation a little bit more simply, right? So what we are saying is that the number of rehashes, or the amount of time required to process the ith element, right, is either 1, right, if it doesn't create a new, if pi is not part of the closest pair, then the time needed to add it is just constant, right? So we can say that with a probability of with the probability of right? So 2 by I is the probability that it is part of, it's one of the closest pairs. 1 minus 2 by I is the probability that it is not one of those, right? So if it's not one of those, then the time needed is just the constant, right? You just have to hash it, put it into the table, check its neighbors, all of this takes constant time, and then you'll find, okay, it doesn't update the closest pair. Then the other possibility is that you have to rehash, which means that you're going to spend order of I time because all the I elements have to be rehashed, and that probability is 2 by I, right? So you can see that this is nothing but 1 minus 2 by I plus 2, right? So the expected time for adding the ith element, right, is just this, which is less than or equal to 3, correct? Because this 1 minus 2 by I the maximum value it can get to is 1. Right? And this I times 2 by I, the I cancels out and it's just 2. So the expected time for adding the ith element, ith point, is just 3. Right? So we have a linear time algorithm, right? Because each point takes only 3 time to insert, and right? And then I feel that if I ask you to code this up, you'll probably say, yeah, I can do it, right? I'm sure if I asked you to code the other problem, you'd say, okay, I'm going to drop the course. Okay, so all it takes is order of n time, and again, the interesting thing is it's not even a probabilistic algorithm, right? Many times when you get a much improved runtime bound, right? Remember, the previous algorithm was not only complex, but its asymptotic complexity was still n log n, right? Whereas this is a linear time algorithm, right? So when you get that kind of asymptotic speed improvement, very often you have to trade off a deterministic algorithm for a probabilistic one. Whereas in this case, it's deterministic in the sense that at the end you do compute the closest pair, right? It's not that with a high probability you compute closest pair. You have the closest pair. The answer is correct. The randomness is coming in only as far as speed is concerned. Okay, so that leads us to the next topic, which is hash table. Right. So what we are going to do in the next, we'll start off the discussion about hash tables today and spend most of the next lecture on hash tables. So hash tables are used to maintain dictionaries, or you can represent sets using hash tables so that you can check, do fast membership check. Okay, but some operations like union and so on are not necessarily fast. So most common case is for a dictionary. Okay, and so typically you want to support operations like lookup, insert, and delete. Okay, and ideally order of one average case. This is what you want to achieve. And what we're going to talk about is how we achieve the average case, because one of the common problems, common pitfalls is that people sort of assume input is random, and then they end up implementing hash tables that become captive to input distribution, and you can very easily get into situations where things, where you see much worse case than the average case you expect. So those are the two questions we try to answer. How to avoid order of n worst case behavior, because we know that hash tables have order of n worst case, right? Somehow, if you chose a poor hash function, so for instance, if you have a string and you said, okay, I'm going to hash a string by multiplying all the characters in it, right? Sounds like a good hash function? Doesn't look too bad. Well, what's the problem? Why? Right. But the problem is actually it's worse than what you might think, because if at any point the product becomes 0, then it will always be 0. So there will be huge clusters forming around 0, and so you really have to be careful in the way you choose hash tables, or else you can very easily get into this order of n worst case behavior. Okay, so we will let's stop here and we'll continue to discuss hash tables next.